Hello there. So today we're going to learn one last type of differentiation technique that will become handy when you go to higher calculus. We call this implicit differentiation. And we will use this when you have functions of a certain type. Okay, so if you're ready, let's get started. Primarily, we will be discussing two types of expressing function expressions where you will need to do implicit differentiation. Okay, the first type or the first case is when the dependent variable is not of the first order. So if you notice, since we began our treatment of the function in quarter one, up until the last meeting, we always see functions written neatly where you have the independent variable, okay, or f of x is equal to, and then some expressions containing only x's. Or you might also see y, which is the dependent variable, is equal to, again, expressions that are in terms of x's. You can have as many terms as you like, or you may even have transcendental functions, but always the dependent variable is on one side, typically the left-hand side, and all the other expressions containing the independent variable are on the right side. Now, functions may be expressed in a different manner. Okay, so take a look, for example, at this case. You have here the case of y squared is equal to x. Y squared is equal to x. Well, sir, actually I can write that, sir, as the dependent variable and into something. For example, that can be rewritten as y equals the square root of x. Okay, but for purposes of showing what implicit differentiation is, when this is the case, when you have the dependent variable that is not linear, or not of the first order. So in this case, you have a second order dependent variable y squared. How will you do the differentiation process? Okay, so watch closely. You will differentiate y in terms of the variable of differentiation, which is x. So you treat it like any normal differentiation process. So this y squared by power rule becomes 2y. But by chain rule, you know that you still have to differentiate the function within the function. So y, you know, is a function, so you have to differentiate that in terms or with respect to the variable of differentiation, in this case x. You are applying here the chain rule. Okay. Why is that something? Why is that something? Now, on the other side, you differentiate x. So that's very easy. That's 1, correct? And then what do? You're looking for the derivative after all, which is dy dx. So you just say dy dx is 1 all over 2y. Now, for implicit differentiation, practically you're done. Okay. Sir, really? Is that the derivative, you might ask? Okay. Remember that in this case, what is y? Y is equal to square root of x. So actually, we can rewrite the derivative as 1 all over 2 times what is y? The square root of x, correct? So you will see that this is our result right now. On this side, we are using implicit differentiation. We used implicit differentiation. Now, let's try to do this, supposing we didn't know what implicit differentiation is. So here you will get the usual, sir, y equals square root of x, so this is x raised to the 1/2. So the derivative dy dx is equal to 1/2 x raised to negative 1/2, or this is 1 all over 2, and x raised to 1/2 is square root of x. But take a look at the results. Whether we did implicit differentiation or we did it with the usual differentiation process that we know, the results are the same. Okay, the results are the same. And we're happy to see, at least in this case, that whether we did implicit differentiation pala or the typical differentiation process that we know, we arrive at the same answer. We arrive at the same answer. Okay, sir, are there other cases where I need to use implicit differentiation? Yes, there's another case. Again, this is something that you are unfamiliar, okay, up until now. That is when the expression has a term where the dependent variable cannot be separated from the independent variable. Okay, so this is very crucial. You cannot separate the dependent variable and the independent variable. For example, take a look at this expression we have here. Y squared minus xy is equal to x. Okay, unfortunately, no matter what you do, for example, let's try taking out y. You'll get y minus x is equal to x. You'll end up with y is equal to x over y minus x. But in doing so, this side of the equation still has a y, or the dependent variable, even if you tried the dependent variable to be on one side, on the left-hand side. Let's take a look at another way of rewriting this, sir. What if you did this? Y squared is equal to x plus xy, and then you have y squared is equal to x1 plus y. So you have y is equal to square root of x1 plus y. You will notice that still there is a y here. You cannot isolate the y from the x's. Okay, so the equation or the expression is not variable separable. Okay, so in these cases, you're left without a choice but to use implicit differentiation. And how do we do that? Okay, so how do we do that? Let's see. Sir, you said I will differentiate y like the usual way that I do. So y squared by power rule, sir, that's 2y, but by chain rule, I know that that y has a derivative, dy dx. For now, I don't know what it is, but it is the derivative of y, or dy dx, minus, okay? And then you have xy. Sir, I will do the product rule. So the derivative of the first function, derivative of x, is 1 times the second function, so y, plus the first function times the derivative of the second function. So the derivative of y, I do not know, but it is dy dx for now. And we're good on the left-hand side. Now on the right-hand side, we derive x. The derivative of x here is just 1. Okay. Now, what we do next is we try to isolate dy dx from everything else. Okay, I think it's quite easy. Okay, so let's give it a try. That's 2y dy dx minus x dy dx minus y is equal to 1. And then we take out, we move negative y from the left-hand side to the right-hand side. We get 2y dy dx minus x dy dx is equal to 1 minus y. And then we take out by factoring dy dx, you get 2y minus x is equal to 1 minus y. And so finally you will have dy dx is equal to 1 minus y all over 2y minus x. Now, what does this mean? This means that this expression, 1 minus y all over 2y minus x, is the unknown derivative that we were writing earlier as just dy dx. Okay, and we were able to arrive at this using implicit differentiation. All right, to see some more examples, just look at the next video.